So when we left off, we had just plotted and discussed a line from simulated data, a regression line that was fit to simulated data. And now we're actually going to get even simpler for this next piece in order to think about the most basic regression that can be done. And we'll see how we're sort of going forward nesting some simple estimates and comparisons within the scope of regression and then sort of build on those. So clean this up. We're going to take, let me see. Yeah, okay, did all of this. All right, so we're going to have a sample size of 200 and set the seed again. You don't have to do that if you want to see how the simulation may vary in the case of the data created. And so we'll have y underscore 0 be a pseudo-randomly generated normal. So we're generating observations from a normal distribution, and they're going to be 200, right? Because that's the n0 with a mean of 2 and a standard deviation of 5. Again, out in the world of statistics, oftentimes the normal parameters are mean and variance, but suitably in R, they take the standard deviation as that second parameter. Okay, so we are going to generate those observations, and if I want to just take a peek, I want to see all, well, 200 isn't that many. Yeah, let's, all right, first of all, let's actually create a data frame, which is a sort of specially formatted kind of matrix that we're using with, where observations are in the rows and the variables are in the columns. Notice that this matrix is just a 200 by 1, right? It's just a fancy vector, but internally it's going to be recognized as this special object, a data frame, which certain kinds of functions will expect. Okay, so I've got this fake generated data. All that's been generated is a bunch of observations drawn as if from a random normal, 200 observations, random normal, mean 2, standard deviation 5. Let's get a sense of what they look at by rounding just to one decimal point and seeing all of that data. All of those data are here, right? So you can see some 9, 13, 6, and negative. We could actually write this ahead, but I could look at things like, let's just do a summary of, let's do y0, the original vector, and minimum is negative 9.8, maximum is 14.55, median, mean. These are randomly generated. If I were simply just estimating the mean of the underlying distribution here, I might come up with 2.431, right? We know behind the scenes that the true mean is 2, right? But we know that a sample mean, even for 200 observations, is not necessarily, in general, you don't expect it won't be exactly equal to the population mean. Yeah, there is, just to reiterate, the mean of this is 2.43, and what am I doing here? And I'm rounding again just to not have too many, I don't have so many significant digits after it. I'm taking standard deviation of those observations and divided by the square root of the number of observations. What is that doing? Well, it's giving us a standard error, right? Because an estimated standard error is a special kind of standard deviation for a sampling distribution. Here it's a sampling distribution of a mean, right? So we had a mean of 2.43 in our sample, but since that's just being used hypothetically to estimate the true mean of the distribution, which we secretly know when we put on our omnipotent, or rather omniscient, both omniscient and omnipotent hat, we play data god, and we know that the true mean is 2. Here was our estimate from 200 observations of 2.3, but here's our standard error, our recognition that, okay, typically when we sample in this way and we have this many observations, we're going to expect to typically be off by around 0.36 in either direction. And that would not actually, in this case, we were off by more than that. But if we had a 95% rather than a 68% confidence interval, it would be 2.43 minus 0.72 and plus 0.72, and that would certainly cover it, as would actually a 90% confidence interval. Again, in reality, we don't know whether our interval is covering or not. And this is really a frequentist point of view of thinking of everything in terms of hypothetical sampling distributions, which we don't actually observe, right? Okay, so now suddenly we're going to jump into a linear regression, and it seems like a non sequitur, but you'll see in a moment why it's not, how it's related to this. So we're going to fit a linear model. I'm going to start by using the Stan GLM package with the Bayesian estimates. And I think at this point, yeah, it's not taking too long. Some of the later examples take a little bit longer. We will use the print function to see some basic information about it. And let me fill more. So what did we do? First of all, let's just look at what this regression was. We were regressing all those y's on 1. What does that mean? Well, if I just put a 1 and it's got 200 observations and it says regress on this single number, it's going to automatically, I could have, created a variable, and perhaps I should have, that said, something like REP 1 and 200 of them, right? So that I have all those. Is that 200? Yeah, it doesn't take up much space at all. But since it's expecting, for each of those y observations an x as a predictor, if you just give it a number, it's going to internally assume that it's just a vector of ones. So you don't actually need to force to explicitly tell it to repeat. So the data it's using is the fake data, which again was just a bunch of observations. I could have created a X column that had a bunch of ones in. We'll see something like that shortly. So what happens when I regress? So it's using just, there's no variation in the X, right? It's just 1, 1, 1. Each time I'm using a 1 to predict Y. So I'm giving it really no information in essence, right? And so what does it do? Let's take a look. It's best guess. It's just an intercept model, no slope, right? So it's like instead of y equals a plus bx plus an error, it's just y equals a plus error, right? Here's the a, 2.4, and here's the median absolute deviation scaled, so give or take 0.4. What does that look like? 2.43, 2.4, 0.4 uncertainty indicator, 0.36 as our standard error before, right? What's going on here? Let's actually do just for familiarity for some folks who have worked in R before, used output using the standard frequentist linear model. Let's do that as well. And what do we get out? Here it is, coefficients, only one coefficient, the intercept, 2.43, a standard error of 0.36, right? Exactly, once we're not using distributing a whole posterior distribution as in the Bayesian one, we're just doing our best, or essentially a least square fit and estimated standard error. It looks exactly like what we got out from the mean of our observations of y and the standard error, right? So what does this mean, right? It's taking a regression. If you regress y onto a constant like 1 specifically, it is the same thing as estimating the mean of y, right? It's not using any predictors, so it's just basically, it's like if you took all the data points and spread them out on the y-axis and there were no x-axis, the mean would be the best guess, right? You would just, if I wanted to guess what the next y was going to be, my best guess, if I want to minimize my really my squared error in my guess, is to just use the overall mean or the estimate of the mean. It's almost so simple it's hard to wrap your mind around. Let's go. The takeaway is regressing on a constant is the same as estimating the mean of the dependent variable. Let's go one step further. Let's take, we're going to have 300 observations. And again, set the seed, same seed as before. And we were going to draw our y, our dependent variable in a regression. There's no regression yet, but we're going to have a variable y1, which has a normal distribution, has mean 8 and standard deviation 5. We're going to draw 300 observations. So we're simulating, we're being the data generating force we're pretending to be. Right? So we did that. We're maintaining our y0, right, which were the 200 observations we centered on. What did we center on? 2, I think. Yeah. We had 2, standard deviation 5. So a different random normal distribution. We took a bunch of observations from there. Now we're taking 300 observations from a different data generating process, also normal. 300 centered on 8 and standard deviation 5. Wider standard deviation, right? Wider spread, more variation, and a larger mean. And now I do want to show you, well, I guess I haven't combined these into a data frame yet, but maybe I'll jump the gun and do that. I feel like I thought I did it later, but yeah, no, okay, it's a slightly different one. All right, so I'm going to take my difference between them. So notice it's not an individual, it's not a mean difference between, this is why I can't have a data frame, because it's just 2 different data sets. I've got one 300 observations, one with 200 observations. I'm just looking at trying to estimate the difference in means between those 2 distributions, right? We know what the difference in means is because we played God. We know 8 is the mean of y1 and 2 is the mean of y0. So the true difference in means is 6. But we are going to take our sample means, sorry, all of this we need, find the difference, and let's actually even, well, we'll do the standard error for each, right? The standard error for y naught and the standard error for y1. The overall standard error is the square root of the sum of the squared individual standard errors, right? And now let's see, what is this? Well, what was diff? The difference in the sample means, right? So what do we get for that? 6.076, right? Not too bad. We wouldn't know this if we were really just playing the part of the researcher. We would just say, hey, 60.76, that's my best guess at the difference in means. Meanwhile, the true difference was 6. So we don't get to know how good it is, but here's our standard error. Our standard error is 0.46. So that is a way of saying my best guess is 6.08, but I expect, the process that produced that estimate, tends to be, loosely speaking, it typically is around 0.46 off, right? Could be better, could be worse. So give or take 0.46, that interval, that 68% interval, my more likely than not interval, will include will tend to include the truth 68% of the time. So I don't know if this is one of those times or not. Putting an omniscient cap on, I do know it is one of those times. Okay, so let's look at a simple regression that's related to this. And you may guess where it's going given the last regression we did. So the overall sample size is 500, the 200 plus the 300. Our y's, we're going to actually this is concatenating, right? Putting a bunch vector end over end, right? When I take all of the observations of y naught and all of the observations of y1, you'll see why in a moment. Just make it easy to create this new pseudo data set. And I'm going to do the same thing with x's, but here what I'm going to do is I'm going to take there are 200 observations of the first y that had a mean of 2, or actually 2.43, but they were drawn from a random normal with mean 2 and standard deviation 5, I think. For each of those, I'm going to have a 0. So I'm going to have my repeated zeros with length of n0, which is 200. And then after that, I'm going to concatenate. I'm going to add on. I'm going to append to it another 300, not observations, but just the 300 ones, right? So I'm going to have 200 zeros followed by 300 ones. We'll see why in a second. These are kind of pseudo predictors. And these are just indicating whether actually if x equals 0, it means you were in the first group, drawn from the first distribution. If x equals 1, you're in the second group. So here's a data frame based on that, putting x and y together. Here's what it looks like, right? Here are some y's from the first group, which I'm saying is the group which I'll label as x equals 0. And then when you get lower, you see all the y values that were drawn from the other group. And actually, I did label them as y underscore 0 and y underscore 1. So all the y1s go with x equals 1, and all the y0s go with x equals 0. Got it? Okay. So we have this dichotomous predictor, which is really just an indicator of which group you were in, and each of those groups had a different distribution for its y. All right, good. So now we're going to fit a Bayesian linear model, y regressed on x using these data. And once that's done, we're going to print some basic results. And what do we get? Intercept of 2.4. Right? How is that useful? Well, we're regressing y on x. It's not especially useful. Well, actually, I guess in this case it is, right? 2.4 should sound familiar, right? It's the value that we expect y to be when x is 0. So it's just really giving the sample mean of that first sample that we looked at, and indeed our sample mean was 2.4. Okay, sorry again, now a different truck is here. But here's the key to the question we had. Slope. What is the slope? 6.1. That should sound familiar. It's similar to the 6 that was the difference in the two means. Right? Let's switch to we've got some indication of uncertainty on these. Here, the uncertainty of 0.5 for the difference, right? That's the median absolute deviation. If we were doing it in a more common form, we've got our regular linear model, and you'd have, hey, intercept 2.43, exactly what our sample mean was of the first pseudo data set that was generated. Standard error, right, give or take. What's the p-value tell me? Nothing particularly interesting. It just tells me that I feel really confident that these two distributions don't have the same mean. It doesn't tell me anything about whether the difference in means is large or small or anything. It's just distinguishable from 0, clearly distinguishable from 0. That's a good sort of low bar that we're reading signal rather than just noise. And what else? Yeah, these aren't especially useful, but the key thing, let's actually plot this to talk about it. And there's a plot with a bunch of extra bells and whistles on it. And so what is this showing me? This is a regression. This is showing me this lesson that we've just learned here, which is that regression on an indicator value, that is an indicator that simply says which sample, which group, which distribution it came from, the 0 or the 1 or the group A or group B, whatever you want to call them, works the same as simply looking at a difference in means, right? So if I estimated, as I did in the beginning, means, and I estimated their difference, and I took the standard error of their difference in ways that we saw last week, we would get the same thing as setting this up as a regression problem, where we're taking the y value, regardless of which group it came from, and regressing it on an indicator value, that a variable that's telling us which group it came from, right? So what do we have? I've got over here on the left, I've got the distribution of y values from group 0, right? Those 200 that were centered on, I forget what, 2 maybe? And on the second one, I've got a bunch of values that had a mean of 8. There were like 300 values. And it's basically trying to, the regression line is really just, a line's going through 2 points, right? 2 points will fix a particular line. This line is going through the sample mean of 2.68 for the first group and the sample mean of 8.38 in the second group. The line itself is not super meaningful other than as a way of connecting those two, but it's, again, a good way to think about sort of the framework. What's the simplest linear model? The simplest linear model would just regress y on the number 1, a constant, and give us a mean. The next simplest is to have an indicator variable, so the only predictor is a 0 or 1 that tells you which group the observation belonged to. And what you get out when you do that is a regression line that has as its slope an estimate of the difference in means, right? That makes sense. Let's think about what's happening with a slope here. A slope is saying for as x increases by 1, what's the difference in the expected mean of y? Well, as you go from 0 to 1, the mean increases, right? There's a comparison difference of 2.43. Okay. So yeah, so that's it for now. We'll do another video in the near future.